All right. So today, today and I'll talk about the following lecture in a while. We're going to look at closing off everything now with some examples. We spent the time sort of leading. We went through the course. We did spectrum analysis. We did filter design. There are two example lectures that you have some material to work on, and we will review that and have enough time to go through everything still before the exam. So today we're going to start looking at some examples in a practical sense, a couple of fairly straightforward examples as to where these things are used. And we can make some sort of comparisons about things that we can do later on as well too. So one of the big applications, as I mentioned before in signal processing, is in terms of being able to generate sort of arbitrarily shaped signals, which is what they call digital waveform generation. The process that we're going to do today is essentially the same regardless of what you want done. But so we're going to focus specifically today on how we could produce periodic signals, for instance, sinusoids, which are the crux of this one. From there, you can move on to others, and we'll talk about that in a while. But digital waveform generation has a number of applications around the place. Of course, in certain things like music and musical instruments, that is the core of how electronic instruments work, in that they generate artificial waveforms that sound like particular instruments, right? So if you can mimic the spectrum of a particular instrument, then you regenerate that, then you can have an electronic version of it, so that you can make, for instance, like keyboards, or if you more have been paying attention, we have a device called a PHY that was created in the Department of Electrical and Computer Engineering. It is essentially it's a synthesizer, but it looks like a steel pan. Right, so the surface on the note layout is exactly like a tenor pan. The full 27 notes and everything in the same note arrangement and so on. But the pads on it, you can program to sound like a whole range of instruments. Of course, most people would program it to sound like a steel pan, a tenor pan, and so on. But you can use it as a full synthesizer. It can sound like a piano. It can sound like a rhythm section, horns, all kind of things inside of there, right? And they use the same process that are much a complicated version of what we're going to talk about today. But it's used around the whole application of waveform generation is used a lot in the music industry. Another way that they use it, of course, is in control systems, that you can generate signals to control motors and valves and so on. So, for instance, like DC motors, brushless DC motors, to have them rotate, you need a particular sequence of pulses to be sent to the motor coils, and you can generate that using signal processing. All right. So there are a whole number of applications in signal processing that are basically centered around being able to generate a digital waveform. So the approach is, let's say we wanted to produce a periodic signal, whatever the shape is, but the easiest one, of course, is a sinusoid, and we'll talk about the rest in a second. Right? A simple approach, in fact, one of the simplest approaches is to design a filter whose impulse response is the waveform. Remember how we spent a couple of times talking about infinite impulse response filters and finite impulse response filters. And the idea is, of course, if you remember, that if you have a filter and you put an impulse in, you get a response coming out. If the response goes on for a very long time, we call it an infinite impulse response. And if it goes on and then stops after some finite time duration, we call it a finite response filter, right? And again, I keep telling you all that in a general, in sort of a general form, instead of the word filter, you could kind of read transfer function here, right? Right, so you can have transfer function. When you see filter, think transfer function. So you put an impulse into it, and you get a response coming out. And remember, a discrete time impulse, this is not the, this is just simply a unit sample, something that goes from 0 to, let's say, 5 volts, a single sample, or 0 to 3.3, or 0 to 10 volts, or 0 to 1 volts, whatever it is. Just a single value of logic 1 comes in, and then the filter does its job. Now, if the output of that is a particular waveform, then we have a way of generating, for instance, a sinusoid. And let's see how that works. So let's say we're required to generate a sinusoid at some frequency f0. So, of course, with everything that we do, I keep stressing this, once in the discrete world, you need a sampling frequency. So let's assume a sampling frequency, some frequency fs. We know that if I want to generate a frequency f0, the digital frequency is 2 pi f0 over fs. And what I want is that hn, the impulse response, should give me something looking like this. Some r to the power n sine omega 0 n. Remember, n is a series of integers going 0, 1, 2, all the way up. So it's going to generate basically sine 2 pi f0 over fs. Okay, the un is to make it causal. This is just, and you'll see why we have this in a little while. This is an amplitude function. So if I is less than 0, then what I produce, first off, we said this is because of this. If the coefficient r is less than 0, what I get is a decaying sinusoid. And if r is equal to 1, this is 1 to the power 1. So I basically have sine omega 0 n. All right? While you would want a decaying sinusoid, let me go to the next slide here. So if r is less than 1, you get something looking like this. This, and depending on the value of r, this can decay quite rapidly. Right? So it can decay, right? Or if you make r fairly close to 1, the decay is quite gradual. Why you would want to do that depends on the particular application that you're dealing with. A decaying sinusoid is the frequency produced by like a tuning fork. If you remember from your physics, when you hit a tuning fork, it will vibrate and the amplitude will slowly decay, but it's producing a nice, clean sinusoid all the way through. It's like a bell sound. So if you want to create a signal that mimics like a tuning fork behavior, then you need that coefficient r to be somewhere between 0 and 1. If you make it 1, then you get a nice continuous sinusoid coming out all the time. Fair enough? Right? All it was, we go back to the formula for generating a sinusoid. And remember this here, this omega naught is 2 pi f0 over fs. And the highest frequency here that I could generate, you remember this thing is, if you remember, the whole thing about discrete sinusoids, they will go up to a maximum frequency and then come back down. And the maximum frequency is fs over 2. All right, all because of our aliasing and Nyquist criterion and so on. So you could go up to, if you pick, I think we said fs was 12 kilohertz for this. No, we just, there's an example later on. So whatever fs is, we can generate up to fs over 2 using this technique, either with the decaying sinusoid or the constant amplitude sinusoid going all the way through. So if I know Hn is this, Hn is r to the n sine omega naught n un. What is Hz? Well, you pull out your Z transform handout, or you remember, you go for memory, and if you have a Hn, this is Hn here, is equal to this. The Z transform of that is this expression here. So if we run it through with our example that we have here, Hz is going to be r sine so and so over 1 minus 2 cosine omega 0 z minus 1 plus r squared, right? And of course, if we want a continuous sinusoid, r is 1, right? A constant amplitude sinusoid. Fair enough? So the step is you pick Hn. Hn is an arbitrary waveform, or the period, sorry, I shouldn't say arbitrary. Hn is a periodic waveform that you want to generate. In our case, a sinusoid. So if Hn is this here, Hz is a Z transform of that. You go to your Z transform tables and you get Hz here. So a little bit, if you go back to what we did some lectures ago, what is a sort of block diagram representation of this? And specifically the canonical representation. Remember, if you go back to what we have been saying, the standard form of Hz is a series of coefficients for the numerator and the denominator, right? A series of coefficients of Z. And if you block it out, right? The representation that we have, the canonical form, means that you put all the delays in the middle. We have the B's. Remember, this is the feed forward. The B's are the feed forward factors and the A's are the feedback factors. And I mentioned to you that you have two ways of drawing the diagram. They sort of, and it varies, okay? So some books, and I've used it here in the slides here, put the feedback factors as minus A1 minus A2, because if you were to cross multiply here and then put YZ equal to B so and so, it will be minus A1 minus A2 and so on when you express Y in terms of X. So the standard form for the block diagram has a minus sign in terms of the factors here. And this is all plus signs here. Okay? Some textbooks and even MATLAB, it varies from sort of in, what shall I say, version to version. Some textbooks would put the A's here exactly as you read it here, and then put the minus signs on the summing junctions. All right? Whatever you do, I am not too concerned if I ask you, or you see in the past papers, or you see in the problem sets, to draw the representation here. You can do it either way for me, but just be consistent. If you use the minus signs, let me just clear the ink here. If you use the minus signs in here, then your summing junctions have to have all positives, all right? If you use the values as they exist straight off here inside, then you need to put a negative sign on top here. Just be consistent. Both are correct, it doesn't matter. Right, so this is the representation, this sort of data flow. So X comes in and Y goes out. And remember, Y is supposed to be our discrete sinusoid here. So let's compare the two. The standard form, and we got this from taking this is the Z transform of Hn, which is, we said, was r to the n sine omega naught n u n. Okay? So if you take the Z transform, you get 8Z. And if you compare the coefficients now with the top and bottom, remember this is, if you compare B0 here, so B0 here is 0. B1 is R sine omega 0. We have 1. A1 is minus 2R cosine omega 0. And A2 is R squared. Right? We go back now. This is the general form. So what we said here, B0 is 0. So you can block out all of them. We don't have any B0. We don't have any. And B2 is, we don't have a B2. Okay? So block out B0, block out B1. And then if you're going in, if you're using it as we have here, right? Minus A1, remember A1 is this. So minus A1 is going to be 2R cosine omega 2. And A2 is R squared. So this is going to be minus R squared. Right? Following? Yes? Yeah, no, maybe? All right. So this is the representation of it. And remember, the input is an impulse. That's how we started this whole thing. If we put an impulse in, and the impulse is just a single value of 1, that's all it is. So 1 goes in, and this thing now is going to generate, because of the feedback loops, this is the feedback here, this is an infinite impulse response. So, and it's going to generate an impulse response that goes on forever. And because the impulse response is a sinusoid, we're supposed to be getting a discrete time sinusoid coming out of here, right? A similar approach, we'll see how that works in a second. A similar approach gives, if you want a cosine signal generated instead of a sinusoid, right? So what I want is R cosine omega naught n instead of sine. So if this is Hn, you go to your tables and you get Hz. And notice this time we have a B0 here. We didn't have a B0 for the sinusoid. Okay? So in this case, we have B0 is 1. All right? So look at the difference here. In this case, for the sinusoid, we didn't have this one here. Remember, this is B0 here. Right? As we said, that doesn't exist. But with the cosine, there's a B0 here, which is 1. Right? So if you want to put B0 is here, this is 1. Okay, so let's see if this works in practice. So the theory is, again, we want Hn. This is the impulse response here. This is the sine or the cosine. The impulse response means that if Hn is, this is, well, remember the impulse response is y z over x z, right? So y z is equal to h z x z. And if xz is an impulse, which is 1, right? The z transform of the impulse is just 1, then yz is going to be the z transform, the impulse response here, which is supposed to be the series of the sinusoid and cosine signal coming. Well, let's see if that works. So I want a 300 hertz cosine digital signal generator. So I want to generate a cosinusoid at 300 hertz. So first thing, I need a sampling frequency. So let's use a sampling frequency of 10 kilohertz. Right? That's kind of plenty above the frequency F0. But what it does, it gives us a lot of samples in between. The sampling frequency of 10 kilohertz. So omega 0 is therefore going to be 2 pi 300 over 10 by 10 to the power 3, right? Work it out. So you have omega 0 here. And then if you go through here and also if omega 0 is that, it's a cosinusoidal. So we put in omega 0 here, we put in omega 0. If it's a cosinusoidal, not decaying, R is 1, right? So R would be 1 here. So this is 1, 2 under Z squared here. So once you do that, you're supposed to get this transfer function. If you get that transfer function now, you could use something like MATLAB, put to generate the impulse response. So you put a 1 into that, and look at what the impulse response looks like. Right? Notice that the envelope is your cosine signal. If you want to confirm if the frequency is correct, then you can do an FFT or ask it to do a frequency response for you. And look at what the response looks like. Exactly at 300 hertz. 300 hertz right here. You have a single clean frequency being generated at 300 hertz and nothing else. Yeah. So this is the impulse response or the waveform that you have coming out. And it is in fact a 300 hertz signal. Make sense? Everybody following? In most cases, people tend to generate cosines instead of sines, although it's 90 degrees off. But for practical purposes, it tends to give you an easier manipulation. Remember sine, if you were to go back to Euler's relationship, a sine, the e to the omega is cosine plus j sine, right? Or cosine minus j sine, depending on what you're trying to generate. That j operator is what gives you the sort of issue with sinusoids all the time. So a lot of the time when people are saying that they're generating sinusoidal waveforms, they tend to generate cosines instead of sines, okay? One application for this is something that has been around for a while. We still use it without even realizing it. And some of you all may have come across it in comms already. It's something called dual tone multi-frequency generation. And you see it on keypads. Every time you press a numeric keypad, like for instance, the 12-digit keypads on a security system to enter a room, right? Or the keypad on your cell phone, right? When you're dialing somebody's number, you will notice that there are 12 keys inside of there. Every time you press the key, what it does is that it really generates two frequencies. That is how the keys are distinguished one from the other, which is why they call it dual tone. Every time you press a button, it creates two frequencies. And the frequencies are a combination of a high frequency and a low frequency tone, and it's mixed, right? And each combination of omega low and omega high uniquely describe which key was pressed. So any 12-digit, as you say, pull up your cell phone and so on. And this is done electronically, so you don't hear the tones anymore, but the cell phone system does it. Right? You hear their tones if you have someone like if you ever see anybody with the older Me Too phones, or if you have one of the phones at home, like a cordless phone still hooked up to B-Mobile or Digicel and so on, when you dial the numbers, you would hear the tones going through. So the frequency ranges, the high frequency group are a bunch of three frequencies between 1209 and 1477 hertz. They're very strange numbers, and I'll tell you why in a second. And the low frequency starts at 697 and goes to 941. These frequencies are very strange. First off, because they're difficult to create randomly. Okay, so it's not something that, like, for instance, somebody whistling could randomly create one of these frequencies and have it recognized by a system. That's the first thing. And secondly, they create tones that are outside of the sort of speaking range of the normal voice range of a human being. So it will not interfere with the audio of speech. And again, the reason being that when somebody's talking, it's unlikely, well, almost impossible to generate this group of frequencies by you speaking to somebody else. So every time you generate, if for instance you press the digit 2, the digit 2 here will generate 697 and 1336 hertz. So those two tones will be generated and it will go down the transmission line. And at the other end, there are filters that are tuned for each of these frequencies here. Right? Each of the frequencies here. So once it filters, it goes into a frequency bank, and depending on which bank produces an output, then you know which key was pressed. Okay? So what would they, if I were to do this, if I'm generating it, then each one of these, right, this is a cosine omega naught n here, where omega naught is 2 pi 1209 over some sampling frequency, right? It depends on the system that you use. Okay, so it is going to have one cosine generator for that and one for 697. So every time you press, so you have, what you have therefore are 4 cosine generators for the low frequency group and 3 for the high. So that when you press the key, and some of you all would have coded a keypad in your microprocessor course already, somewhere in the lab. So when you press a key, it reads the keypad matrix is read, and depending on how it decodes it, it will know, okay, let's mix the 770 signal with the 1477 signal. 770 and 1477 mean that somebody pressed the 6th digit, and you send it down the road, right? And even the asterisk and the sort of hashtag, the pound sign symbol also have their own codes as well, right? So HZ is therefore, for instance, let's say for the 4-digit, just for that would have to have a 770 signal and a 1209 signal being generated. So 2 cosine, right? One for the one for the 770 and one for the, what is it? 770 and 1209, right? So we'll have one here. So this one would be 770 and this one would be 1209 hertz. Okay? And typically, I mean, it's audio, they probably, I think the sampling frequency is 8 kilohertz. They can use higher sampling frequencies as well, right? So that for a typical note, remember we're going to mix a low tone and a high tone. We have 4 of these, and we have 3 of these. So every time you press, and this is where the key comes in, when you press the key, all the key is doing is putting a 1, right? A logic 1, whatever the voltage is. As it goes into the system, that 1 generates, depending on which key was pressed, it mixes the low tone and the high tone, and you get the dual tone coming out. Yeah. So you have 12 combinations to deal with. Make sense? So the application of this is that, one, you can generate sinusoids, cosinusoids by looking at what Hn is, what is the Hn that you want the impulse response, and then getting Hz from that. And then you can sort of go up and down the frequency range to your heart content. If you put the attenuation factor, then you get a tone that decays. And then if you use it in a particular application like we have here, you can use it to signal, to send unique signals between devices. In this case, it's a tone signaling, which is used all the time, right? And even in the cell phone system, as I said, it's disguised in the background, but it's still there. And just to quickly mention, now we started and said, well, what about, let me just go back to the beginning. What about, for instance, triangle and square waves? The same, you can use a couple of approaches for this. Remember, these are computer generated signals. So you have a couple of things you can do. One of the things here is both the square wave and the sine wave. You can use what you have learned before about your Fourier series. For instance, you know that sinusoids, odd sinusoid frequencies with certain, and if you vary the amplitude, you can create any of these by a suitable combination of sines and by sines and cosines, and suitable and the phase relation with it. So once you could generate one of these, if you know, for instance, I want to generate like a sawtooth, what is the Fourier series representation of this? And once you know what the Fourier series representation of this is, you recreate that by creating the various sinusoids and cosinusoids and then just adding them up. These are all done, remember, it's a processor that is doing this. So you can generate as many as you want to your hearts. These are as many, what do you call it, harmonics as possible, right? Typically, to get a good to get a good ramp or a good square and so on, you probably have to generate like 15 to 20 harmonics. But it's a simple thing. Once you generate one, the programming aspect for generating one sinusoid is this. This is a single sinusoid right here. All right, let me just put it up here. This is a single sinusoid of frequency omega 0. So if I wanted to generate 2 omega 0, 3 omega 0, up to 50 omega 0, the process is still the same, right? Just put them together, and as the impulse comes in, it generates all of them together, adds them up, and you get your particular waveform being created. Triangle, ramp, square wave. You can do it as many as you like. All right, so it's the same process. Once you know how to generate a sinusoid, and you know from your Fourier series that a sinusoid can be used to create a whole range of other periodic signals, then you can generate virtually any periodic signal that you like once you can find the Fourier series representation of it in terms of sine, well, which will give you it in terms of sines and cosines. Yeah? Make sense? All right. Okay, so that's it for today. The other lecture, now Wednesday is the day when people have to deliver this their 3020 project, and Monday, I believe next Monday is when I think Monday and Wednesday actually I am supposed to be doing the presentations, the examinations of some 3020 projects, right? So the next lecture following this, which is in fact the last lecture of this series that we have, I have a recording of it. So I'm going to put up that recording for you all to listen to. It's very simple. It's on JPEGs and how JPEGs work, which is another application of this. It uses transform techniques for this. The recording has both today's lecture, so you'll get a double whammy. You'll have that one because I did the recording for both of them together. So you're going to have today's lecture again and lecture 22. I'll put that up for you all. And so Wednesday, you're doing homework, right? So we won't have any class on Wednesday. And during the course of the week, I'll let you all know what we're doing next week. All right. We actually are ahead of time. We're in week 10 now. So between week 10, week 11 is the 30-20 week. And we have weeks 12 and 13 now to do, we'll do a complete course review, do all the remaining problem set 3 years up, do the past papers and so on, and answer any questions that you have. You'll get back the in-course exam results in between. I'll bring back the papers and give you in class. So we'll do that one face-to-face, and we can run through everything. All right, so we ahead of time. So now the thing is really for you to start reviewing and doing this stuff yourself. All right? Okay, so I'll let you also, no class on Wednesday. We will, there's a recording for Wednesday's class, and we will take it from during the course of this week. I'll tell you what the schedule is looking like for next week. What we can do online, and then what we'll be doing the following week, which will be week 12. Okay? Everybody all right? Okay. Let me